Okay, so I come back to the systolic array. So our starting point is a DG because DG gives you a very regular pattern. You know, regularity is very important, very useful for VLSI relation. All this we discussed many times. But normally a DG could be capital N dimensional, and that capital N comes from the number of iteration indices. Like, you know, for the 2D DG we drew for FIR filter that had two indices. One is time index in the N, another was that filter coefficient index J, B0, B1, B2, something like that. So we had two iteration loops. In general, capital N number of iteration loops may be there. So those N indices correspond to N x's. Okay, so it's an N dimensional space in general. You got a DG, every point is filled with a node, and nodes are common, the same node, just repeated. One of the axis is time axis implicitly, and since that cannot be realized in practice, okay, because it's N dimensional, in real life I can only implement up to third order, up to third dimensional. Okay, so I have to map that entire N dimensional DG to either 3 dimensional or 2 dimensional or 1 dimension. So it could be a transformation from N dimensional DG to a 3 or 2 or 1 dimension, right? So in general then N dimension to capital M dimension, M could be 3 to 1. We will consider that, but then for this course I will very soon switch over to N to N minus 1 dimension transformation. So it could be 4 to 3 or 3 to 2 or 2 to 1 kind of thing. So if it is 4 to 2, you can even apply it twice in succession, 4 to 3 and then 3 to 2. But in general it should be N to M, but that is more general, that requires more linear algebra kind of stuff. Okay, and more complicated. I am just trying to give a flavor of systolic array, and many problems can be done with this approach. Okay, so what is our starting point is a DG, N dimensional DG. Any point there is a coordinate vector. You can write in a vector form also in the classical vector algebra mode. In the vector algebra, you have done 3 dimensional vector algebra, I axis, J axis, K axis, but you can make it N dimensional. So a vector at any point has a coordinate, and you can write it as a vector form also, column vector form. Capital N into 1 length, n points. So that means suppose you are given a DG, one node, I show by a dot, its coordinate vector is IN. IN is, I am not so bothered about the components of IN, but it is an n dimensional column vector, because it is n dimensional space. So there are n x's have got n coordinates. So maybe you can write IN1, I am giving the subscript n to indicate that it is coming from here. IN2 dot 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 INN. I am not so bothered about these elements. This is writing for, I will not get into the elements at all. I will write using this notation, with the subscript will indicate the length of the vector or dimension of the. Suppose in the DG there is one node, there is another node somewhere. It is an n dimensional world. I cannot draw an n dimensional thing on a 2 dimensional paper. So that is a limitation, but you try to imagine that way. Okay, it is somewhere in that n dimensional space. And it is Jn, so another coordinate vector, and there is an edge here. That DG has an edge from IN. So from IN the edge immediately goes to Jn, no node in this path. This edge also is a vector after all. If you see the coordinate here minus the coordinates here, then you get E. That E basically will be a vector when you start at the origin, isn't it? Get 2 dimensional. So you got say two coordinate vector, you just subtract one from the other, you get the edge vector, but that then you are referring with respect to the origin. This you understand, isn't it? So this is that En. What is En? Jn minus In. So wherever is the origin in that space is, En will correspond to a vector. Again, length n. Okay, n dimensional world. En also is a vector. I am treating it as an edge vector. I am adding it to this, so I am getting here. Since it is a DG, it is regular, it is repetitive. So then from Jn also, if I go on adding, if I add En further, to please note one thing, that if you read Paris book, you want to get any of this. He suddenly starts with a definition, asks you to do some operation. Now no explanation, nothing. So please take your note very carefully in this today's lecture, next lecture also. Okay, here please be very careful. Okay, and I won't make it in, I won't dilute the rigor and all that. So whatever I am doing, I will try to give you proof and all that. Okay. So you are suppose adding this edge to Jn. So that will definitely take you to another node. This is DG after all. You remember the 2D DG, one node going to another edge, taking you to another node. The same thing repeats. So if you add that edge, you get to another node as per the DG. These are valid connections. Okay. It will take you to then say another point Kn. It may not be adjacent point. It is not that every coordinate here is just coordinate here plus 1. Don't think that they could be adjacent. I want them to be close, but that is separate matters. It is not that to this you add 1, to this you add 1 and like that you get J n, not like that generally. But this edge, if it is E n, most important, this edge also E n, because it is d g, it is repetitive, it is regular, this is very important. Okay. Now, I told you the n dimension is too high, I cannot realize anything more than 3 dimensional in real life, so I have to bring it down. So, I have to bring it down to m dimension. M in, I know in the back of my mind m could be 3 to 1, but for the time being I am trying to be general. So, I am mapping it to a lower dimensional space called m dimensional space. I will map. So, each node will be mapped to another node in a lower dimensional space, m dimensional space. These are objective. How and all and what are the constraints or what are the other things that will come up in that process, that is what will evolve down. So, I will be mapping it to, maybe I will be mapping it to, this is just mapping, and mapping transformation I say f. F will work on I n, give you I m in an m dimensional space, I m, which is nothing but some function, mapping function of I n. If I am, this mapping function is my choice, I am applying this to all the nodes and getting m dimensional output, fine. J n also will go to J m f j n, sorry, and this also will go to k m. Whenever I put an underline, means actually vector. Sometimes if I miss out, this is just by mistake, okay, because scalar and vector coordinates, when I am writing both, to distinguish between them, I write an underscore, okay. So, I might be mapping, but my computation, my processing won't, I cannot allow to change. So, earlier if the result from I n was going to J n, I am mapping this in a lower dimensional d g, but processor remains same. So, the same output should reach here also then, otherwise the purpose is gone, isn't it? Processing is gone. So, that means there can be a new edge here and there can be new edge, but these two edges may not be same. It depends on how cleverly I have chosen f. If I am choosing f arbitrarily, erratically, this could go somewhere, this could go somewhere, this could go somewhere. I mean, you cannot say that whatever I have between this and this, that will repeat here. But there may be some, that edge is required, otherwise my processing will be lost, because earlier after the node generated output, it was passed on to this guy, and when this is processed and output generated passed on to this guy, same thing I have to repeat here also, otherwise the processing chain is gone, isn't it? But these edges may not be same. Now, I want to make life much more simpler than this. Consider J m. J m is f j n, and what is J n? J n is I n plus E n. Suppose I want this function to be linear. If it is linear, f of this is f of I n plus f of E n. Suppose when f linear, the same thing is equal to, linear functions, f of I n and f of I n I know, f of I n is here I m, and plus this guy f of E n, you can give it a name also, E m, you can give it a name E m. This particular E n I have taken, f of that, or this E n is a vector, f of that I also know, I am giving it a name E m. What is the advantage then? If I now want to do f of k n, what will be f of k n? What is k m? And k n is j n plus E n, f is linear, so it will be f of j n plus f of E n, which is j m plus the same guy E m. So, that means if this edge is E m, this also is E m, and regularity prevails here. Here the same edge was going on, you are getting node, another node, another. The way the connections were, the same thing will prevail here. Regularity will prevail, same edge vector. Mind you, in two-dimensional world only you see the vector, but in n-dimensional world not only magnitude, direction is important. The moment you change coordinate of a vector, direction also changes. But if I do this trick, if I assume it to be linear, only EM is important. You just map it to a new point, to that you add EM, you get to the map of this. You add further EM, you get to the map of this. Go on adding, okay. So the regularity thing prevails, and most importantly, I, like a mad guy, don't have to find out if you define f by applying f on each person and giving you the result. I have to I can define f by simply telling you the output of f when f works on the edge. So if the original DG, and every DG is defined in terms of few edges. You remember in the 2D DG I have shown you there are some basic edges. One was going in this direction, one was vertical, another was this angular. 3 vectors, 1 0 0 1, 1 minus 1. So if your f is, if you define your f on these 3, finished. In the new space you fill all the dots, all the coordinate, integer coordinate points with dots, the nodes, and to them you add these edges, new edges, that is mapped edges. Okay, this is understood. So we will prefer f to be linear then, and therefore f of one particular edge vector is enough for me. If I know that EM to all the mapped version, you just map one node to its n-dimensional space and go on adding that vector. You hit upon new nodes. This will then be map of this, this will then be map of this, next one will be map of this, like that. Okay. If originally it was regular, the regularity will prevail here. There will be no chaotic thing, no erratic thing. Okay. Regularity is very important, that will be preserved, because originally it was DG, DG is regular, and I am mapping it linearly. So edge directions won't change. Edge directions define the regularity, otherwise it is just a space of nodes. There is no connection, it is a space and nodes. That is not what it is. There are edges and still it was regular, the pattern was very regular there. If similarly I maintain the edge connections that way, the same edge only repeats, the original regularity will manifest here also. You can see this, no? Okay, so we will prefer it to be linear. If so, then immediately it raises these questions. F is what then? F is a function which takes an n-dimensional real vector, in fact vector I am taking a real, but actually it is integers, but do not bother about integer real, because each coordinate point in my case are integral points, either 1 1 or 1 0 or 2 1 or 2 2, like that, but for the time being let us assume real case. Okay. I will take a real from real case and then apply here. Or suppose I consider R n. Theoretically it should be Z, Z is set of integers, Zn to Zm, but permit me to extend it to R, but we will only consider integers. I will do this modification little later. This is the mapping after all, this is a general mapping. What is Rn? It is a vector, n-dimensional vector. What is Rm? M-dimensional vector. What was f doing? It was taking a coordinate vector of dimension n, giving one output m length m. But we have chosen f to be linear. We have added one more thing, f is not just arbitrary function, it is linear. Then what is f? Any vector, any operator, any map, any function that takes an n-dimensional vector and gives an m-dimensional vector and is linear can have only one structure. I will show this, I do not know your background well. So, that structure is nothing but a matrix. Very simple, I will show. F will be a matrix of dimension m cross n. I am first writing F is equivalent to a matrix. This is a matrix. Huh? I prefer notation T for matrix, but the book for some reason has brought P. So, I am just, he in fact writes P transpose. God knows why he brought a transpose there. He can write the matrix to be P. Okay. So, I am P cross n. This is my claim. F in this case will be nothing but a matrix of this, my claim. Okay. And I justify the claim here. These are very simple things. How to get P? First I form a P and then I will show that this operation is done perfectly. This F operation on this Rn vectors to get to Rm can be defined exactly by this. If you choose your R m comma n perfectly. F is given to you. I am saying F can be represented perfectly by a matrix. My claim is, please understand my claim. What is my claim? You gave me a F, but that was vector to vector, like a table. This vector goes there, this vector goes there. I say that I can represent that F by a matrix exactly, equivalently, completely, so that you give me a vector Rn, I will simply multiply that vector, pre-multiply by the matrix, I will get a length m vector. My claim is that will be the map of that Rn vector under F. That is my claim. So, I will choose a matrix accordingly, and it is choosable, it is obtainable, and I will show that. Okay. And therefore, instead of showing F like this, vector to vector, which you cannot do in the infinite vectors, I will simply write F in terms of a matrix, and then you give any vector, matrix will multiply the vector, give you the result of the map in this Rm. Okay. That is very simple. Suppose I consider one vector, I consider n number of vectors, capital N number of vectors from this Rn, very specifically chosen. You will learn little bit about matrix, manipulation of matrix and all here also. Okay. Forget about systolic arrays. If you do a course of mine on adaptive filters, you will learn a lot of linear algebra, which you have not done. Then you will see the connection of all that to our subject. It is more of electrical engineering today, linear algebra and vector space, than of mathematics. So, alpha 1 I define one vector, n dimensional. Alpha 1 means you start with 1 and then fill in zeros. These are called trivial vectors actually, trivial basis vectors. Alpha 2, in general alpha I 0 0 0, then 1 0 0 0. This is the ith position. Okay. How many such vectors are possible? Capital N number. 1 0 0, then 0 1 0 0, then 0 0 1 0 0. Last one is alpha n. This is very simple, isn't it? How many vectors are possible? See the structure. First, alpha 1 means 1 at the top and zeros. Alpha 2 means this 1 comes down, 0 then 1 then zeros. Alpha 2 means 0 0 then 1 then zeros. So, finally, at the nth step 1 will move to this last position. So, you get n vectors. If they are linearly independent only you can see, because when one has 1, others have 0. So, others cannot be linearly combined to get that. That is a separate matter, I am not mentioning here. Suppose I form the matrix P, I am not writing P m cross n anymore. I just permit me to drop this subscript, because it is the same P, but I am just dropping the subscript just for convenience. Others have to go on writing so much. Okay. Suppose I put these column vectors like this, it becomes a just a minute, I made one, just a minute. Actually, this there is a problem. There is a problem because it is not n cross n. Just a minute. This will not work. No. Actually, something more is required. No, something basis, something I was trying to avoid that, because alpha 1, if I go like this, because it is a m cross n, so its number of elements should be m. So, if I go like this, I need to construct a better proof for this. I will do it in the next class if I cannot construct in the limited time. This is m cross n, m cross 1 say. How many you can have? M, isn't it? But this is a m cross n matrix. How many columns you need here? You need n columns, isn't it? So, this will be, if I cannot just place alpha 1 to alpha, okay, I cannot just place alpha 1 to alpha n, because then it will be a m cross n square matrix. Okay, I suggest that it needs little background of basis. Maybe I complete it in the next class, because if I start thinking on it, I will spending 3-4 minutes wasted. It will be a P m cross n matrix. How the matrix comes, let me see. If it comes to my mind, I will tell you. because maybe I can tell. Okay, I will come to this later, little later. I will come to this little later. Okay, it is a m cross n matrix. What it does is it takes a vector. At least this will be a linear operator. This you can see. See, one way to see that if I give you this will be a linear map. You start with this. The fact that it is the linear map, there is no other linear map possible. That I will come to later. I was trying to prove that. Okay, we need a notion of basis and all that. You are familiar with basis and space spanned by a set of linearly independent vectors, then the set of linearly vectors, that number is called dimension and that set is called basis. Those kind of things will be required here. Okay, I just have to organize the proof in my mind. But suppose you start with this. There is nothing wrong if this is linear, we see. Suppose we take f like this, m cross n. Okay, then what is my argument? This matrix will work on a m length vector. I will give a proof, do not worry, I will give a proof, but it will work on an m length vector, n length vector, give you an m length vector. This is a linear map. Okay, so that will at least do our purpose. I was looking for a linear map. Suppose I take the linear map like this, that will do our purpose. Then comes an issue that this is m cross n and m is less than n, we know, m is less than n. So, that means number of row is less than number of columns. My point is you choose this matrix so that there are m number of linearly independent columns. You know linear independence and dependence things, no? If a set of vectors is linearly independent, then you cannot write it as a linear combination of the rest. If I give alpha 1 to alpha say p or alpha 1 to alpha m are linearly independent, the way to test is c1 alpha 1 plus c2 alpha 2 plus dot cm alpha m. If you get to 0, only way you can satisfy this is by that choice c1 equal to 0, c2 equal to 0, like that. No other solution. You know all this, little bit you know. Okay. So, suppose I choose the matrix so that actually technically speaking, I should say that it has a submatrix within this matrix of size m cross square matrix, that is full rank of rank m. That actually in my terminology means that we choose the matrix so that there are m number of linearly independent columns. You cannot have m plus 1, you know, because if this length is m, if vectors are of length m, you can have m number of maximum linearly independent columns, and this space is span a space which is dimension m. You know this much. M number of, if the length is m, then you can have maximum m number of linearly independent columns, not more than that. Anybody else can be written as a linear combination of these things, you know, isn't it? So, I construct the matrix so that there is one submatrix, square submatrix of size m cross m, which is full rank of rank m, or means which has got linearly independent columns. All the m columns there are linearly independent. Okay. Just for ease in my presentation, suppose I take that on the left hand side, there is no problem, isn't it? Just for the ease in my presentation, this is that matrix. Overall matrix is P, say this is A, and suppose this is B. A is m cross m, full rank, and this guy is B. This is your how much? N minus m cross A, n minus m, isn't it? Okay. Now, suppose I want to solve an equation like this, P x for some x equal to 0. Here you will find non-zero solutions of x. You know, actually if a matrix is full rank, square and full rank, one way to test is this, that if you solve an equation like this, suppose P is square and full rank, the only solution possible there will be x equal to 0. I will not get into all that, I will be dragged into more of linear algebra, you know, and I like linear algebra very much, so I will be speaking more on that, so there will be deviation. It is just an certain extra tips I am giving, not required here. Okay. In general, suppose I want to solve that equation where P has this structure. This x vector I can always write as x a upper half and x b lower half. X a is of size m, x b of size n minus m. I am writing a because a will work on it, I am writing b here because b will work on it. Okay. Then this p x is nothing but, you know, a times x a plus b times x b. I can write this. Okay. you can choose, the our purpose was to solve for x. Okay. I am saying x equal to 0 is always a solution, but that is not the only solution in such case. If there are infinite solutions for x which are non-zero, which will solve this under this structure of P, where m its length size is m cross n, this is m cross n, which is full rank. That is what I am proving. But suppose you want to solve it, I break it like this. Okay, this is square full rank. Suppose I start with arbitrary value of xb. There are some components in xb, arbitrary value, and then I get a vector here bxb. Since A is square and full rank, by solving I can find an xa. A inverse times this will give me a solution. So I get a solution for x. Next time you change xb, you get another vector. Again you get solve for xa. You get another vector. So that way there is infinite choice, right? So at least this shows that under such structure you have got infinite choice of these vectors, which when put to Px give you 0. These vectors actually come from what is called the null space of the matrix P. Null space. I am telling you what is null space is. Again, you know, I mean, I should not be dragged into linear algebra. In some other course, yes, but here not, because it is an VLSI course. But null space is this, that suppose I am solving this Px equal to 0. You found one solution x1, so that Px1 equal to 0. Found another solution. I told you many solutions are possible, and they are non-zero solutions, say x1, x2, 0. That way you can find many solutions. I am now suppose looking for solutions x1, x2, those solutions which are mutually linearly independent. Okay. See, there are so many coming up. I will try to find out, okay, I got this. Am I getting another one which is linearly independent? Okay, so I collect the two. Then again I look for third guy which is linearly independent with these two. So I will get a finite set finally, which will be linearly independent. If I consider the space spanned by that linearly independent set of those vectors, that space will be called the null space spanned by those vectors. And number of that vector will be called the dimension of the null space, which is called the nullity of the matrix. Okay, nullity of the matrix. Okay. I am not writing too much on that, because I will be finally going to that n to n minus 1 transformation. There things will be much simpler. Okay, but this is a general case. I am presenting a general case without giving you proof, but just to have your, I mean, tune your mind to this. So what is happening? I first proved the existence of many non-zero solutions previously by solving it in that xa, xb kind of pattern and all that, and you choose your xb, you get an xa. Choose another xb, another xa. Since infinite solutions are possible, I say find a x1. Again, then find another x2 which may be linearly independent with x2. Then one x2, x1, x2, try to find out. There is a way to find out. You don't have to search in dark, but you find out another x3 which solve this. But again, x1, x2, x3 form a linearly independent set. This way, if you build up, finally, because of the finite nature of the matrix and all that, you will get a finite set of such vectors only, which are linearly independent. And so they are span. They will space a span. Span means what? Set of the linear combinations, all possible linear combinations of this vector. That is called the span, or space spanned by this. That space is called the null space of this matrix. Okay. Why it is important, you will very see. I am not just doing mathematics, you know. Why it is important, you will see very, very soon in the systolic thing. Null space. So the null space will be spanned by those few basis vectors. That basis, the number of that basis vector is called the nullity, and that space is called the null space of the matrix P. Fine. Each vector there will be of what length? Length n only. Now suppose you are mapping one node in to in by working P, that matrix, on that in coordinate vector. You get one. Suppose, just for fun, to that in coordinate I add one of the vectors, any vector from that null space. So I get some other node. What I am saying is this: suppose this is in, it takes you to im, and you take a x from the null space of P. That means P of x, meaning P of x is 0. And any vector, there are so many infinite choices possible. What I do now, for just fun, suppose x is length n, this is length n. Suppose I go somewhere here, which is in plus x. On that again, I apply the same operator for mapping. Where will I land on? I will land on here. That means many nodes, theoretically infinite nodes of the original DG will map to one node in the resulting DG. That means many nodes of the original DG have to be executed by one node. So, their execution times, I will do the scheduling, times should be different. I have to schedule those node operations by the single node here in such a way that different. Do you see this? Because of this thing, that is m cross n and m is less than n, it is a rectangular matrix, not a full rank matrix, its rank is only m, not up to n. You get a situation where you find infinite set solutions for p x equal to 0. If p were a square matrix of full rank, only solution for x was 0. P inverse 0 vector is 0, fine, but that is not the case here. So, I have got an infinite solution for x, and any such solution I add to in, I get back here. Okay. So, you see this in the general case also, many nodes, in fact infinite number of nodes of the original DG map to one node. Now, I come to the my simpler case of n to n minus 1. From now onwards, it is n dimension to n minus 1, and that proof I will give you. I will just organize the thing in my mind. I mean, okay. One way is to prove with the general case, but knowing your background, I will tailor it so that it is a concise proof. I mean, it does not require other theorems and all that. That is the kind of proof I offered in the previous year, I remember. Okay, I thought it will come up, but I find there is this thing. So, I will give a proof of this, that this is the only linear map. If I am looking for linearity, this linear map will be represented by a matrix. There is no other possibility, and this will work on a vector, multiply this, give you the result of that map. That proof I will give you maybe in the next class. Okay. Now, I come to our original goal of, I mean, from n dimension to n minus 1 dimension, and n in most of the cases will be what? Will be, could be 4, so 4 to 3 or 3, so 3 to 2, 2 to 2 1, like that. Like our DG was 2D DG. But maybe before I do that, let me complete another thing before I do that. There is another aspect. This is called mapping of processor space or DG to a lower DG, okay, mapping or projection. I call it projection, projecting one DG to another DG. There is another aspect, as it was given in the title, that is called scheduling. Let me do the scheduling also in the general framework of n to m dimensional transformation. Then both I will view in the n to n minus 1 dimensional transformations. Okay. You understand? I have done the projection in the general case where you transform an n dimensional DG into a m dimensional DG. I will do the scheduling also now. What is scheduling will come, and once I do the both, then I will take up both again in the special case where it is n to n minus 1 dimension. Okay. So, I again go back to that n to m dimension general case and do the scheduling. Scheduling means again, if you take in and suppose there is an edge and takes you to Jn, En, Kn, En. Okay. These edges indicate what? Dependence. Dependence of this on this, not the other way. In does not depend on Jn as per this diagram. Jn depends on In and Kn depends on Jn. The dependence relation is shown by the edges. Okay. That means, in a real life computation, if I give some scheduling that okay, either in this diagram or maybe when they are transformed to the lower dimensional space, this node, if I say that okay, I will execute this node or its map at this point of time, or this node or its map at this point of time, and this node or its map at this point of time, it should be such that the time for this should not precede the time for this. Time is called schedule here. So, schedule for this should not precede the schedule here, and schedule of this should not precede the schedule of here. In fact, I would rather have it this way, that schedule of it should be after this, so that I put a delay to implement that, and therefore, critical path reduces. That is a separate matter. If the schedule of this I choose to be say 1 cycle later than schedule of this, evidently this will imply that I have to put a delay there. That will have that positive effect of bringing a delay, means pipelining, critical path reduction and all that. So, I would rather have it that way, that schedule of this, if it is dependent on this, schedule of this should be greater than or equal to schedule of this, preferably greater. Schedule of this must be greater than or equal to schedule of this, but preferably greater. Greater means if it is greater by 1, 1 delay. If it is greater by 10, 10 delay. Okay. So, that will be my kind of goal. So, scheduling means as I transform it to m dimension, to each of those map nodes I will assign some time index, integer. Okay. At that time only there will be, because no longer there will be a time axis, because what I am going to do, that will be the IC, that is what will be implemented. There cannot be one axis as time axis, but in a separate table I have to write down the relative timing of them, who is executed before whom, who is executed after whom, that is scheduling. So, the time axis will disappear now, which means time information I have to store somewhere about their relative scheduling, who is first, who is second, like that. Okay. So, as I move then, so again suppose scheduling will be a map for IN, it will give a schedule, but earlier n dimensional vector was mapped to a n dimensional vector, because these are positions, n dimensional, m dimension. But when here is schedule, schedule is only a time index, so only one number, a scalar. So, it will be mapping from n dimension to 1 dimension, not n to m, because here this output after mapping, what you are mapping, defining a mapping function S, S for scheduling, S will work on IN, give you one number. This is not a lower dimensional DG, do not confuse with that. I am again defining a function that will work on each coordinate, each node, give you a respective schedule. Schedule is just one parameter, one time integer. Okay. So, I will get one number, that means it will be a mapping from n dimension to 1 dimension. Okay. Here also, so if I call it the schedule, say T1, Tn, sorry, Tn, okay, no, sorry, Ti, here Tj, here Tk, that means what? Ti is S of In, Tj is S of Jn, Tk is S of Kn. Once again I will apply the same philosophy. This is as such, the way I have defined here, S is arbitrary. Okay. But now I will impose a structure on S. What is Tj after all? S Jn. What is Jn? In plus En. If S is linear, if S linear, then it is simply S of In, which is Ti, plus S of En, if you call it tau. So, you understand? Same thing I am doing. If S is linear, what is important is if you know S of this edge vector, and you call it tau, tau amount of time, then schedule of this and schedule of this after mapping in that lower dimensional space, they will be separated by a tau time. Then schedule of this and schedule of this also will be separated by tau. So, again the regularity thing comes. If tau is 1, I will have 1 delay in this edge after mapping. Then in the map of this edge also will have 1 delay, map of the next also have 1 delay, regularity prevails. Okay. But I would want the tau to be, in fact tau should be greater than or equal to 0, must, because dependent shows that this must be completed, then only this can be taken up. So, the two schedules should not be such that this precedes this, so tau should be greater than or equal to 0, but preferably tau greater than 0. Tau could be 1, that means 1 delay, tau could be 2, 2 delay. Delay will cut down the critical path, that is a separate matter. So, I would, in my design I would try to schedule so that S of the respective edges is just not greater than or equal to 0, it is actually greater than 0. So, I can take 1, 2 like that. Okay. Another important thing as valid there also, that then to define S, I like a madman do not have to define S over each node, because entire thing I am doing is based on the edges. If you take En, if you know S of that, that is tau, that is all. So, along this line you know what is tau. So, if there are a few fundamental edges in the DG, you find out S of each of the edges, so you know the time delays or this schedule gaps between nodes along those edges. Okay. So, S also I take to be linear, but S is linear means earlier it was n to m dimension, n dimension to m dimension. So, it was an m cross n matrix. now it will be 1 cross n matrix. It will, let us say, row vector. So, S is nothing but a row vector here. We call it scheduling vector, row vector. That will multiply a column vector, this coordinate vector, give you a scalar number, which is integer, because S vector, all components I will choose to be integers only, and this has components integer. So, when you multiply such row and column, you will get an integer. Okay. So, this is scheduling, and scheduling S, we know the structure is a row vector, but positively that S transpose the edge, any edge should be greater than equal to 0. That is a must, because edge defines dependence, is not it? So, the destination node, its timing, its schedule should not precede that of the source node. That is the fundamental, that is the main thing, preferably greater than 0. Now, I combine these two in my special case of n to n minus 1 dimensional case. So, that means this matrix, Paris book writes P to be P transpose. I suggest you do not follow that. This P, previously I wrote P m cross n and then I dropped m cross n, but Paris writes P instead of P transpose. Okay, I do not know which book or which thing is following, but let us make it P. So, P we know, P will be n minus 1 cross n. And since S is a vector, I write lowercase now. Lowercase underline is vector, uppercase underline is matrix from now on. S is just 1 cross n. Okay. I concentrate on P now. I concentrate on P. How to choose P? I give a constraint like I did before. You choose P so that you have a square matrix of size. Earlier it was m cross m, now it is n minus 1 cross n minus 1, which is full rank. It is n minus 1 cross n. So, you choose this matrix, P matrix. One condition is that you choose it such that maybe this part, you can call it A, this is full rank, rank n minus 1, and then you are left with one column only, you are left with one column, is not it? Because this way you have got n columns, so n minus 1 taken, so this is A, this I call B. Since this is vector now, instead of uppercase I indicate by lowercase. Okay. Here again I try to do the same thing as I was doing for null space and all that, but this time it will be more concrete. That time I used some notions, I relied on your the understanding of bases, dimensions and other things, but now it will be more concrete. It will not require any background. Okay. Suppose again I want to find out this equation. If this is P, I have to solve an equation like this, Px equal to 0. Since again it is n minus 1 cross n, by the same philosophy as we did earlier, there are infinite solutions are possible. Okay. How? Once again it will be like A x, if you break up x like x a upper part and maybe the lower part is x b, is a scalar x b, then it is b times x b, right? And you give any value of x b, you give any value of x b, you get a solution for x a. Again give any value of x b, you get a solution for x a. That way infinite solutions are possible. But one thing, in this case all those solutions are linearly related. One is just a multiple of another, which would mean that null space has dimension 1, it is spanned by one vector. Okay, this I will show. I do not want to get into the general linear algebra first and then prove it. So, this is a very special case I have taken n to n minus 1 dimension, there I can prove it easily. Okay. Suppose you start with you take this x, I told you you have to take x b. Suppose you take x b to be 1, you solve. Okay. B, this was given to you, this is part of the matrix, I cannot change small v, I cannot change a, but x b say you take 1, you solve, you get a vector. Next time is x b is say lambda, that solution is will be what? Lambda times the previous solution. Are you following me? If you put 1 here, solution is minus A inverse B. Next time you give it lambda, any number, lambda. Lambda is a scalar, you can keep it separate. So new solution will be lambda times previous solution. So all solutions were just some multiple of that only one solution. Okay. Also, one can even ask, if you are very clever mathematically, I would have expected a question like this, that sir, you are taking like this, but suppose in a matrix this part is linear, full rank, but it could so happen that this part also, if you take this part or some other square matrix, that is also full rank. Then in that case, what do I do? In that case, you will consider A to be a vector, B to be a matrix, okay, and then this becomes a scalar, this becomes a vector. You give say 1 to here, you get one solution, then you give any lambda, lambda times that solution. But those will be new set of solutions, it might appear to you. And earlier I got 1 here, I got a solution, and other solution lambda times this. So these two could be two different solutions, set of solutions. This is not. I suggest that you argue it out. Okay, this is not. Did you understand my question? Okay, it will not, because even if you solve this way, put the solution here, put your any solution you obtain here, you again consider this, when you do the p times that solution, you consider this matrix partition like this, as we did before, this part and this part. Once again you solve that way, that will turn out to be a multiple of what we had here. Okay. So that means essential thing is here, if I solve for p x equal to 0, all solutions are what? Just a scalar multiple or only one basic solution. Okay, one basic solution. So that solution I call say x equal to d. It could be any solution, say x equal to d. D is called, I don't know why it is called a projection vector. When you choose D, remember I am now, even though I have written a matrix of real numbers and all that, basically they are integers. When you choose this D, you can either take it to be say, whether D or 2D or 3D or 4D or whatever, they are all solutions for this equation. But you try to take the D which is having the minimum weights, 1, minus 1, thing like that, not 2, not multiple of 1, not multiple, okay, which has the minimum norm actually. That way I call it a basic vector. Other solutions are integral multiple of that D. Okay, so this D will be called projection vector. That means In plus this D and In plus 2D dot dot dot. That is why I told you take D to be the one with the minimum norm. So In plus D, then the 2D comes, then 3D. They all will map to the same node, because P working on this, P working on this, P working on this will give you P working on simply In. Okay, it will give you P working on In. So this is the thing. When it is n to n dimensional case, I have a very special case coming up. I choose the matrix P so that there is a square submatrix of dimension n minus 1 n minus 1 of full rank. Immediate fallout is that here null space has got dimension 1. That is, all the solutions of this equation are what? There is multiple of a basic solution. That basic solution I call x equal to D. Earlier it was not so. Earlier the null space I told you there may be one solution. You remember I told you that time that there may be one solution x for px1 equal to 0, there may be another px2 equal to 0. You try to find out so that x1 and x2 are linearly independent. Then look for another solution px3 equal to 0. Then x3 should be linearly independent with x1, x2, x3. This is why I said that you consider all the possible linearly independent solutions for this. Okay, a finite number will come. Consider the space spanned by them. Okay, that space was called the null space. Any vector there was actually not a multiple of x1 only or not a multiple of x2 only. It was a linear combination of those basic linearly independent vectors. Okay, now it has become lot simpler. It is simply a multiple of only one vector. That is the thing I have made now because of this n to n minus 1 transformation with that square submatrix present of dimension n minus rank n minus 1. I have now reached a situation where all solutions of these are just multiple of only one basic vector. So, dimension is 1. Okay, dimension of null space is 1. That is why everything is fine if I know the basic D. Only this in only along this line in the original DG, only along these nodes you find out D. D is a unique vector. No multiple D's are possible, only one choice of D is possible because of this. Find out the D, to in you add the D, then 2D. Mind you, these nodes, their locations in the original DG, they may not be having an edge. D is not an edge. Please understand, D is not an edge. D is a vector coming out of the solution. So, in node and another node located at in plus D, there may not be an edge between them, but these nodes map to one node after transformation. Okay. This is coming because of the rank deficient structure of this matrix, because I am going from higher dimension to lower dimension. Okay. There may not be an edge between them. Don't confuse D with an edge vector. D is not at all an edge vector in general. So, this is one thing, and in the case of scheduling vector, we have seen that dimension will be 1 cross n, and the constraint is, there is a constraint on the choice of S. What is the constraint? S transpose E for any valid edge of that original DG must be greater than or equal to 0. That is one constraint on the choice of S. Another is, I have cut it, I should never cut it. These vectors in plus D, in plus 2D, they all I know map to, there may not be an edge linking them, but they all map to same node. Okay. That means the schedule for this must be different, because they are all to be executed by one processor. So, at the same clock cycle it cannot do the job of this or this or this together. Okay. That means S transpose this vector, what is the schedule of this? S transpose this coordinate vector. Sorry, it is not S transpose, I will write S, because it is already in a row form. SE, or if you permit, I make it, I know I love column vectors actually, not row vector. I am very happy with the column vectors. I make it 1 cross n. Instead of column row vector, I call it column. So, it is S transpose E. And what is the schedule of this? What is the schedule of this? S transpose this coordinate, S transpose this coordinate. Instead of row vector, I made it column vector, because I am more conversant with column vectors actually. Normally, I deal with column vectors. So, otherwise, I might make mistake here and there. So, column vector. So, actually, it should be transpose. Then it becomes the original row vector. That row times, that is S transpose times the coordinate vector, that will give the schedule of this. So, schedule of this is S transpose in plus D, and schedule of this is S transpose in. This must not be same. This means what? S transpose D must not be equal to 0 scalar. Because the schedule of this and schedule of this, they are at a gap of only S transpose D, that much amount. S transpose in, then S transpose in plus S transpose D, S transpose in plus 2 S transpose D. The factor here is S transpose D, that must not be 0, then all the schedules will coincide. So, on the choice of S, these two constraints. E comes from the original DG edges. Looking at the DG, you know what are the edge vectors, basic edge vectors, and you choose a P, that P gave rise to a D. Depending on your P, from this situation you find out what is that D. D is to be found out from the choice of P. D is to be found out from the choice of P. There are clever ways of finding out, even by intuition and all, by visual inspection one can find out. Once you know the D, S should be chosen such that S transpose E for all the edges of the original DG must be greater than or equal to 0 and S transpose D must not be equal to 0. If it is equal to 0, these nodes all will have the same schedule, so there is a conflict. So, in the next class I will then use this and take up examples. First I will try on the 2D DG of FIR filter, but then I will move to a more meaningful problem of 3D DG or matrix multiplication and all, and I will develop systolic arrays for them. Okay, thank you very much.